All right, so today we're going to talk about the introduction of the T statistic. So, the T statistic is an alternative to using a Z score. So, when you have your sample mean, it estimates or approximates the population mean. So, we've got the standard error that will describe how much of a difference is reasonable to expect between a sample mean and a population mean. So those two formulas can indicate what that looks like. The T statistic can also be an alternative to a Z score in that Z scores quantify inferences about the population. And you can see the formula there of how that might be represented. We can use the unit normal table to find the critical region if the Z score forms a normal distribution when we have less than 30 participants, or when the original distribution is approximately normal when distributed. The problem that can exist sometimes whenever we have a Z score is that it requires more information than researchers typically have available to them. It requires knowledge of the population's standard deviation, which is needed to compute the standard error. It also requires that researchers you have only the sample data. Well, the researchers are only going to have the sample data available, and it needs more than that. So the T statistic could be considered an approximate Z score. So we've got the standard error, which is used to estimate the actual standard error when the value of standard deviation is unknown. This can be computed from the sample variance or the sample standard deviation, and it can also provide us with an estimate of the standard distance between the sample mean and the population mean. So our estimated standard error would be S squared to estimate standard deviation squared. And that formula would look like just like you see on the screen. When the value of the standard deviation mean is unknown, we will use that estimated standard error because it's based on variance, um, and the sample variance is an unbiased statistic. The T statistic uses the estimated standard error in place of that standard deviation. The T statistic is used to test the hypothesis about an unknown population when the value of the standard deviation is also unknown. We can also have computation of the sample variance, which requires computation of the sample mean first. Only n minus 1 scores in the sample are independent. Researchers would call n minus 1 the degrees of freedom. Those degrees of freedom will describe the number of scores in a sample that are independent and free to vary, noted as df equals n minus 1. And then we can also have a family of distributions, one for each possible number of degrees of freedom. And that will give us an approximation of the shape of the normal z-score distribution. When we have a flatter than normal z-score distribution or a more spread out than normal z-score distribution or more variability and fatter tails in the t distribution, that could give us the approximate shape of the normal z-score. So we would have to use a table of values of t in place of the unit normal table for the hypothesis test. So if you look here in figure 9.1, we can see what that distribution of the t score would look like if we had degrees of freedom at 20, at 5, and then what a normal distribution looks like. So we get those approximations. Here's the t distribution with the degrees of freedom at 3. So when we want to make a hypothesis or do an hypothesis test with that t statistic, we have to have one sample t statistic, which assumes the null hypothesis is true. And that formula would look like the formula you see on the screen. So all of this here. In figure 9.3, we've got the basic research situation for the t-statistic and the hypothesis test. When we know the population before the treatment is provided, and we're looking for the unknown population that exists after the treatment was given. We can also use the t-statistic for hypothesis testing through the use of 4 steps. We can first state the null and alternative hypothesis and select an alpha level, usually 0.05. We can locate the critical region using the t-distribution table and the value of the degrees of freedom. We can calculate that t-statistic and then make a decision regarding the null hypothesis. So if we look in figure 9.4, we can see that critical region for the t distribution with alpha at 0.05 and the degrees of freedom at 8. The assumptions of the t-test are the values in this sample that must consist of independent observation. So we have the population that's sampled, which must be normal. And when the sample size is relatively large, this assumption can be violated without affecting the validity of the hypothesis test. We also could have the influence of sample size and sample variance. The larger the sample, the smaller the error. The larger the variance, the larger the area. So a large variance means that you're less likely to obtain that significant treatment effect. And then it can also reduce the likelihood of us rejecting that null hypothesis. So let's go ahead and do a learning check. When we have a small number that's less than 30 in the t distribution, which would be truer, A, B, C, or D? I'll give you a few moments to think about it. And that correct answer would be B. It's going to be flatter and more spread out than a normal distribution. Let's also look at a couple of true false questions. By chance, 2 samples selected from the same population that have the same size, like 36 people, and the same mean, 83, that means they will also have the same t statistic. Think about that. And then compared to a z-score, a hypothesis test with a t-statistic requires less information about the population. So I'll give you a couple moments to think about both of those two ideas. And then we've got false for the first one. The two t-values are unlikely to be the same. Their variance estimates will differ between their samples. And the second one is true, that t-statistic does not require the population standard deviation. The z-test is what requires that population standard deviation. So when we measure effect size for t-statistics, we have the hypothesis test, which simply determines whether the treatment effect is greater than chance. Chance is measured by the standard error. There's no measure of the size of the effect if it's included, and a very small treatment effect can be statistically significant. Therefore, the results from a hypothesis test should be accompanied by a report of the effect size, such as Cohen's D. So when we get ready to estimate Cohen's D, we have to use the original equation, which includes the population parameters. However, the population mean with treatment and standard deviation are both unknown. So that estimated Cohen's D is computed using the sample standard deviation, like indicated right down here using this formula. Here's an example in figure 9.5 of the sample distribution of scores in samples 9.2 and 9.3. We can also measure the percentage of variance that's explained using R squared, and that's an alternative method for measuring the effect size, which is used to determine how much of the variability of scores is explained by the treatment effect. So we would use this formula. We would say r squared equals the variability accounted for by the total amount of variability that exists. So we could look here in figure 9.6 and we could see those deviations when there was no treatment effect for the scores in sample 9.2. We also need to be able to look at confidence intervals as well, and those are alternative techniques for describing the effect size. These can be based on the reasonable assumption that our M should be near the other number. And then the interval constructed defines the near based on the estimated standard area of the mean. This can help us confidently estimate that where things should be located in our study for our statistics. Every sample mean has a corresponding t-value, which is defined in the equation, and we can rearrange that equation as well whenever we're trying to calculate the amount of variance. In any t-distribution, values are going to pile up around 0 for any standard deviation that we know. The proportion of the t-values are going to fall between plus or minus t for the appropriate degrees of freedom. And you can see that example, which we can be 95% confident that a sample mean corresponds to that t in that interval. If we look at figure 9.7, we can see the distribution of the t statistics for the degrees of freedom, which are 8. Then for constructing that confidence interval for any sample mean, we'd have to pick the appropriate degrees of confidence, use that t distribution table to find the value of t, solve the rearrange equation, and have our resulting interval, which would give us 90% confidence of that interval. Sometimes different factors, though, can affect the width of the confidence interval. If our desired confidence level is there, then we are going to be more confident in what we desire, and the width of that interval will increase. When we're less confident, the width of that interval will decrease. So if we have a large sample size, we're going to have a smaller SE. If we have a smaller sample size, we'll have a larger SE. So when we get ready to report the results of the t-test, we're going to report whether or not the test was significant, and if we rejected or failed to reject the null hypothesis. We'll also report that t-statistic value, including the degrees of freedom. We'll report the level of significance as well. When we have non-directional two-tailed tests, those are going to be most commonly used. However, directional tests may be used to explain the investigation or pilot studies. We have to also use those 4 steps of a hypothesis test to make sure that those are carried out so that our critical region is defined in just the one tail of the t distribution. So figure 9.8 tells us what that one-tailed critical region of the hypothesis would be if our alpha level was 0.05 and our degrees of freedom were 8. So let's go ahead and do another learning check. The results of a hypothesis test are reported as follows. What was the statistical decision and how big was the sample? They give you a few moments to think about whether A, B, C, or D is correct. And hopefully you came up with B. The null hypothesis was rejected using a sample of N equals 22. Here's also some true-false questions. The sample size has a great influence on the measures of effect size. And when the value of the t-statistic is near 0, the null hypothesis should be rejected. Give you a few moments to think about both of those. And for both, we have false. And measures the effect size. Measures of the effect size are not included to any great extent by influence by the sample size. And when the value of t is near 0, the difference between those two scores is also going to be near 0. So I hope this gives you guys a better understanding of Chapter 9 when we want to include that t statistic.